I'm happy to introduce the today's speaker, Pablo Soberón, and he will share. Pablo Soberón from New York, working at Borsuk College, and he will share with us today some truth about mass partitions. So please, Pablo, we are waiting for the talk.
All right, so first of all, thank you for the invitation. I'm happy to be here today to tell you a bit about some research work I've been doing with a few students about mass partitions, and I want to focus on two things. One is how they relate to transversals and to Stiefel manifolds. I'll define all of this in a few moments. But before I begin, let me tell you that this is joint work with Ilani, Axelrod-Freed, Michael Manta, and Yuki Takahashi. They're all undergraduates. I started to work with Michael before he started college at Caltech, and Ilani and Yuki they work with me during a summer program we have here at Borsuk. And I will mostly focus on the work we did, so that I did with Ilani and with Michael. And if I have enough time, then we'll also talk about what happens with the work with Yuki, which is also related, but this is sort of the collaborators in this work. Okay, so let's start with the topic of the day, mass partition, and really what do we mean by a mass partition problem? So the main idea behind the mass partition problem is I'll give you a few measures in a real space, in this case in the plane in R2, but it could be in higher dimensions. I'll stay with real spaces for the moment. And what we want to do is, if I give you a few measures, I want to split not the measures, but the space itself. So I want to split the underlying space onto pieces so that they satisfy some nice properties. In this case, I could, for example, split R2 into 3 convex pieces, like this angles here. And if I tell you that I want a partition of this type, maybe you can do it so that each part has 1/3 of each measure. In this case, the orange region here is not being split correctly because this is less than 1/3 of that measure. But maybe you can find a way of splitting things that doesn't cause a problem. Okay, and so the main vague type of question we're working with is, if I give you geometric constraints on how to split RD, say 3 convex cones or in the plane or something more elaborate, what can you tell me about how you can split families of measures? How many measures can you split evenly? Or what can you, like, maybe in some cases you want something that looks like this. Maybe I don't really want, I want to cut a regular pentagon, and I want the regular pentagon to do something with this. Okay, so it doesn't have to be, all pieces have to be equal. Sometimes you want something different, but this is more common where you want something equitative between the pieces. Okay, so the overarching thing that happens in this problem is you have usually 2 really big focuses here. One is when you work with continuous measures where they are smooth and things are easier to, if you move the partition continuously, then the piece, what you get from each piece also changes continuously, which is really nice. Or you could have discrete measures concentrated on finite set of points, and people are also interested in that from the point of view of computational geometry. Many people like convex partitions, or maybe having at least one interesting convex piece. Polynomial partitions, or partitioning using the zeros of a polynomial, are usually also very used because they have applications on additive combinatorics and incidence problems and things like this. If you're dealing with discrete measures, you often care about algorithmic results. If I give you n points in total and they have 7 colors, how many operations do you need to do to find a partition that satisfies the geometric constraints and the combinatorial properties you want? So if if you're dealing with discrete measures, algorithmic versions are really interesting. With discrete continuous measures, you're usually looking at existence results. So in that case, you just want to guarantee the existence of this partition. And of course, if we move higher than the plane, high dimensional results are always nice. And we know much more in dimension 2 and 3. Sometimes because what we can prove happens in dimensions 2 and 3 doesn't happen in high dimensions. But if it happens in high dimensions, we usually want to extend to those. And this is a type of results that have really been worked on for quite some time. And recently, Edgardo Rodan Pensado and I, we wrote a survey on these things. And when you write a survey, a very nice thing is when you get the references, if you're writing them in later, you get a zip file. And so it's very easy to write a program that just checks the publishing date of each reference and plots them. And so this is roughly an overview of the area at a glance. So it shows, of course, it's biased towards recent years, but I would just claim that this clearly shows that the area is growing and it's exciting to work here. And if you're interested in these problems, there are plenty of things for you to get involved in this one. Okay, good. So let me just give you the message of the talk. The message of the talk, I'll define later what Stiefel manifolds are, but what I want to convey is that they are very useful to solve mass partition results. And even if you're not proving something new, it usually simplifies quite a bit the existence proofs you have here. Okay, so hopefully you can. This is what you should use to test whether this is a successful talk or not, whether I convince you of this point. Okay, so let's start with history and first examples. But the classic example for this is if I give you two measures in the plane, instead of having this strange partition with 3 convex regions, what I want to find is a line that splits each measure by half. This is what's known as the ham sandwich theorem, because I can think of this measure as cheese and this measure as ham. And so I want to divide both ingredients by half like this. So this is, it works in high dimensions. It was conjectured by Steinhaus, and the proof he presents, he attributes it to Banach. And it says that the higher dimension you go, the more ingredients you can have by a hyperplane. If I give you D measures in ORD, then there's a hyperplane that simultaneously has each other. And Steinhaus really was a meat eater, because you can see that his motivation was splitting a piece of ham so that both people would get the same amount of meat and the same amount of bone and the same amount of fat, I think, something along those lines. So one corollary of this is that if we go back to the plane, if I give you just one measure, so instead of, I would usually be able to do this with 2 measures. If I just give you one measure, there are 2 lines that split the measure into 4 pieces of the same size. And the proof is quite simple. You just divide using a horizontal line by half. And then I'm going to claim that this is the ham and this is the cheese. And then I apply the ham sandwich theorem. And there's a line halving the top and the bottom, which is 4 pieces of equal size. Okay. Now, if I look at the intersection point of these lines, this is what I would call an interesting point for the measure. It's a point that is in some sense very deep inside the measure, because if I give you any half plane that contains this particular point, then it contains at least one of those 4 regions. In this case, it contains this one. So every half plane that contains this special point contains at least 1/4 of the measure. And if you've seen this sort of problems before, you might say, oh, well, maybe this 1/4 you have here is not optimal. If I just care about this property, you can get away with a probably better point. So this is not longer necessarily the intersection of 2 halving lines or 2 lines that split into 4 equal pieces, but it's a point that every half plane that contains it has at least 1/3 of the total measure. And so this is my half plane. And so in high dimensions, this also exists. It's what we call a center point, where if I'm in ORD, there's a point so that every half space that contains it has at least 1/d + 1 of the measure and 1/d + 1 is optimal. Okay, so we no longer have these two special lines intersecting here, but it satisfies its properties. So these are some very classic results in the area. And if we move from the plane to dimension 3, let's see what we can get in this case. So now I'll have this measure, which is looking sort of like a bowling pin. And if I project this measure down to a plane, I can notice that I can get whatever I get as my projected measure here. I could, for example, split it into 4 equal pieces using 2 lines. And then if I take the inverse of this projection, what I get is 2 planes that divide the original measure into 4 equal pieces, or I should say 4 pieces of the same measure. So this is an extension of, or a trivial corollary from the things I've been telling you, that for any measure in R3, there are 2 planes that cut it into 4 parts of equal measure, okay? And if instead of taking here the intersect, so there's 2 lines, I take the center point of the measure, what I get is a line so that any half space that contains it has at least 1/3 of the total measure. So this is what we call a center line for the measure. And so we get this guarantee here. Notice that in dimension 3, a center point guarantees 1/4 of the measure, but a center line guarantees 1/3. So those are good. And of course, this is just projecting, applying something to the plane and projecting back. So you might say you're wasting some degree of measures, because the plane you're using to project onto, you could choose that in any direction. So maybe if you choose the plane, the direction of this plane carefully, you can get away with a bit more than these trivial corollaries. And this is actually something that people have already done. Hadwiger in 1960 got a version of this one, where he saw that if I give you 2 measures, you can always find a common pair of planes that divide both of them into 4 equal pieces. So for any direction, in some sense, of the projection, you get a pair of planes for the red measure and for the yellow measure, and at some point you get them to coincide. He actually wanted to prove this result I mentioned about 2 lines intersect, cutting the region into 4 equal pieces. In dimension 3, you might think, oh, if I give you 3 planes, maybe you can cut it into 8 equal pieces. And this is one thing that implies that, because if I just give you 1 measure, you can cut it into 2 using a halving plane. Actually, let me make this a bit more permanent. And you call the top the ham and the top the cheese, or the bottom the cheese, and then the 2 planes that cut both the ham and the cheese into equal pieces. Now, those 2 and this new one, they give you 3 planes that divide the measure into 8 equal pieces. Okay, but it's basically this result for 2 measures. I don't know Hadwiger's proof. There's a newer proof by, I think, Blagojevich, Frick, Hasse, and Ziegler, where they use a degree argument, and it's quite nice, and it proves this result as well. And you can ask the same thing for center lines. This is an instance of the central transversal theorem, which I'll come back to later in the talk. But Shivalchevich and Vrechika, and independently Dolnikov, they proved that if I give you 2 measures in dimension 3, there's a common center line to them. So I cannot choose the direction of the center line anymore, but there's one particular center line that's common to both. And one of the first things I did with Michael was to think about a combination of these 2 results. So the way we combine them is the following. I give you 2 measures, mu1 and mu2, and then I can find 2 planes that cut mu1 into 4 pieces of the same size, but the intersection of the 2 planes is a center line for the other measure. And so this really combines the 2 previous results. One thing which I like about this is, if you think about the case Can I do this? Yeah. mu1 equals mu2. Then the previous two results are completely trivial with that assumption, because you just do the results for one of them, and it also splits the other one. But in this case, when the two measures are the same, it's not completely trivial, because you would want for this bowling pin the two planes to cut it into 4 equal pieces, but if every half plane containing the intersection line to have a measure of at least 1/3 of the bowling pin. Okay, so that's one of the results I'll tell you about, and I'll come back to this when we start seeing the proof. Now, the other one, the other family of results I want to talk about today is regarding extensions of the Ham-Sandwich theorem when I have more measures than I should. In this case, if I give you these 3 measures, I cannot find a line that splits all of them by half, because if I cut the green and the red, I certainly cannot cut the blue. So we have to look for a different way of getting. If I want to cheat and get more measures than I should have, I either have to impose conditions on the measures, or I have to do something different. And this is where where mass assignments come into place. So think of the following scenario. I have this 3 families of objects in dimension 3. I have a sphere, I have 2 red lines, and I have this green blob floating. Okay. Now, any plane I take here in dimension 3, I can look at the intersection of the plane with the 3 objects or the 3 families. It will give me maybe the empty set if it doesn't intersect one of them, but it would give me a disk, a blue disk. The lines, they might become pairs of points, or a line and a point, or usually it's a pair of points. And the green blob, it might give me another green blob or a set of green blobs. So what I get is, in every plane, I'm going to get 3 measures. And so my question is, if I allow you to choose this plane any way you want, can you get it in such, can you always guarantee that in some case, the 3 measures you'll have, there's going to be a line that has all of them? So that's the freedom I'm getting extra from the usual Ham-Sandwich, is that I get to choose this plane appropriately. I'm going to allow you to take any affine plane, so it doesn't necessarily have to go through the origin. Okay, and so this is sort of the big question here, and this is so we define a k-dimensional mass assignment as a way to continuously impose measures on k-dimensional affine spaces of RD. So you could do this by intersections with objects. It could be projections of measures in RD, or it could be just an arbitrary continuous way of doing this in the standard. So you get a measure on each k-dimensional affine space, and as you're moving this affine space continuously, your measure changes continuously. Okay. The motivating example for this was actually the case of families of lines which would induce discrete measures, because that was related to a conjecture about splitting families of lines in dimension 3, which sort of motivated this definition by Patrick Schneider. And Patrick Schneider actually proved a Ham-Sandwich type result for mass assignments. So if you give me many k-dimensional mass assignments, as many as the dimension of the big space, there's going to be a k-dimensional affine space where they can all be halved simultaneously by a codimension 1 affine space. Okay, so if I'm doing this in dimension 17 and I'm looking at 2-dimensional affine spaces, at some point I'm going to be able to divide 17 measures by a single line in that plane. And this turns out to be optimal in this here. So what Ilani and I wanted to do was to do this, but instead of having many mass assignments of a single dimension, having mass assignments of multiple dimensions at the same time. It makes a lot more sense if you work with an example. So I'm going to give you the following example. I'll give you 3 measures in R3, 2 two-dimensional mass assignments, and 1 one-dimensional mass assignment. Okay, so every plane, I'm assigning it 2 measures. Every line, I'm assigning it 1 measure. So if I'm looking for ham sandwich type results for this, I can notice, oh, I have 3 measures. I can certainly find a plane, which I'll call S2, that halves the 3 measures by half. Now, in S2, since I gave you 2-dimensional mass assignments, I'll have 2 measures on this S2. So I can apply the ham sandwich theorem in this plane again and get a line, which I'll call S1, that halves both measures inside S2. And now remember, I should have one one-dimensional mass assignment. So inside S1, I should have another measure. And I should be able to have a point S0 that halves this. So what I end up having is a sequence of affine spaces, S0, which is a point, inside S1, which is a line, inside S2, which is a plane, so that each of them has all the mass assignments on the next one. So it's a flag of nested affine spaces of dimensions 0, 1, 2, so that each has all the measures it should be have. Okay. The question is, what if I misremember this example? So I was going to give you the example, but I somehow got it all wrong, and I got 1 measure, 2 two-dimensional mass assignments, and 3 one-dimensional mass assignments. So I can certainly find S2 that halves the measure. I can certainly use the ham sandwich theorem to split the two-dimensional mass assignments. But now here, instead of having 1 interval, I should have, in this line S1, I should have 3 mass assignments, and I'm not completely sure that they will all share a median, those measures on this line. So this, it's usually very easy to split 1 measure with a plane. So the question is whether the freedom I'm getting here to choose the first plane can make up for what I'm missing here that the ham sandwich theorem doesn't give me. Okay, so is there always a flag like this where each of them has all the measures on the next one, even if I gave them in this different order? 3, 2, 1, that's ham sandwich, ham sandwich, ham sandwich. This one, then I'm messing with things a bit here. Okay, and this is the thing that we actually proved. We actually showed that this happens regardless of which permutation of those numbers you give me. So I take a permutation of the numbers from d, d minus 1, d minus 2 up to k, and I give you PD measures, PD minus 1, d minus 1 mass assignments, up to PK, k-dimensional mass assignments. Okay, so I'm going to permute the numbers I would be able to split trivially by using ham sandwich, ham sandwich, ham sandwich, ham sandwich. And then you're going to find a full flag of affine spaces so that each of them has all the measures on the next one. And this is the first result. I'm going to show you the proof. And this is what Ilani called the fairy bread sandwich theorem. I had no idea what fairy bread was until I Googled this. And it turns out that people do this. So they put sprinkles on ingredients. And it shows a bit what you can do with this, because it's like splitting your ingredients with a plane. But when you look at the cut, you care about the position of the sprinkles of the different colors. And you want them to satisfy some properties so that you can cut again and cut again and cut again. And this took me sort of through a rabbit hole of YouTube videos, because apparently people like to do this with baking. I think panda bread is the most usual, where if you cut a bread, you want to have a panda face drawn on it. This is one of the most extreme examples I found, where this person wanted to make a bread so that when you cut it, you would see something similar to the Starry Night by Van Gogh. in this case, it really, I think this shows a bit more what we were trying to do, because you'll have here 3 measures. You'll have this measure of the dark blue, the measure of the light blue, and the measure of the things you'll have here. And you want to maybe cut the breadth in half so that when you cut these things, there's a halving line for this 3 measures on the breadth that you see on the cut. Okay? Questions so far? All good? Okay, so I'll move on to what are the usual, or what are the proof methods, and how do we get to approach these things, and why are those 2 type of results, what do they have in common? Okay. Before I do that, if you consider the permutation, this particular permutation, so you're splitting 1 fewer measure each time than you should be by the Ham-Sandwich theorem. At the end, you're splitting d k-dimensional mass assignments. So this actually implies the Ham-Sandwich type result by Schneider. You just have a bit, like, you have more freedom because you can get away with splitting all these things on the previous subspaces. Okay? Okay, so let's go to proof methods. Every time you see something like this, you see a slightly different proof of the Ham-Sandwich theorem depending on what you're going to do in the proof. So let's go through the Ham-Sandwich theorem. What is one way to approach this? And so what I'm going to take is, in RD, I'm going to take a d-1 dimensional sphere, the sphere that lives here. And for every direction on the sphere, what I'm going to do is take 1 hyperplane perpendicular to V that has the breadth measure. So I'm going to say that the breadth measure is mu d. That's the I have mu1, mu2, mu3 up to mu d. And I'm going to take one that splits. So I just slide it until I do this. I call the side on the direction of the A, and the other side I'm going to call it B. And so this is mu1, this is mu2 in this example. And then we're going to make a function from the sphere to a real space, where for each of the other d-1 measures, I'm just asking which side has more measures, mu1 of A minus mu1 of B, mu2 of A minus mu2 of B, up to the last one I have here. Okay. Now, one cool thing about this function is that if I flip V, the halving hyperplane I have here is the same. Or I should say a bit more precisely, I can choose it to be the same. I can always choose among all the halving hyperplanes the middle one. So I have a continuous choice. I have the same choice if I flip the vector V. And then I'm just changing the name of A and B. So if I change A and B, all of these entries, they just change sign. And so you get this equality here. So it's an odd function. And of course, the Borsuk-Ulam theorem tells me that any continuous odd function from a, in this case, d-1 dimensional sphere to a d-1 dimensional real space has a 0. And having a 0 means that all of these things are 0, which means that this hyperplane was halving each of the measures. The d-1 I have here, because I get the zeros, and the d measure, the last measure, because that's how it was chosen. Okay. So if you want to, a very productive way of approaching this sort of things is to modify the structure of this proof. And this is what we call a test map scheme, where if I give you a mass partition problem, the first thing you do is you parameterize the space of partitions with some topological space X. Actually, you don't usually want to parameterize the whole space of possible partitions. Maybe parameterizing just a subset is enough. In this case, SD-1 is our space, and we're only parameterizing the partitions that already split mu d. We're not getting all possible hyperplanes in this case. And then you describe how the measures are split, maybe using another topological space Y. This was our real space in this case. And it's usually just a real space telling us how much you have of each measure, or which is the largest size, or things like this. And so this induces a map from X to Y. You give me a partition that's a point in X, I'll tell you how it's splitting the measures that's a point in Y. Now, if you have some symmetries in your problem, such as flipping the side of the hyperplane, you'll have a group G acting on both spaces. And the way you're trying to construct these things is that this function is equivariant, meaning that f of gx is gf of x, where this is the action of the group. Okay, so it plays nicely with the action of the group. And then maybe you want to use general properties of equivariant maps from this space to this space to tell you something interesting about the mass partition problem you started with. In this case, it was Borsuk Ulam, implies that there is a partition like we wanted. Okay, if you have a nice topological result that you can pick off the shelf and use, that's usually what you want. Otherwise, you have to maybe adapt some of the result and see what you have. Okay. So let me describe the type of results and spaces we're going to be using for the terms I told you about. And we're going to be using as a space X, instead of a sphere, what I mentioned in the title, the Stiefel manifolds. So the Stiefel manifold with parameters K and D is the set of ordered K tuples of orthonormal vectors in RD. So they're all unit vectors and they are pairwise perpendicular. Okay, so all the possible K tuples you can have here. I like to think of it this way, where if I want to choose V1, I can choose it from a sphere SD minus 1, and then V2 has to be perpendicular to V1, so it's in the equator in the sphere, and this would be a point in V2 of R3. For K is equal to 1, this is a sphere. We just choose V1. And the dimension of the space is also easy to compute. It's just the sum, because if we look at V1, we basically have a D-1 dimensional sphere of options for V1. Then V2, since it has to be perpendicular to this one, it's basically inside that D-2 dimensional sphere. And if we keep choosing them like this one by one, being perpendicular to all the previous ones, the last one has a D-K dimensional sphere to be chosen from. And so this is why you get a dimension of the space of this size. Now, we mentioned that it was important to have an action of a group here. And so the group I'm going to be using is Z2 to the K. I like to think of Z2 as the pair -1, 1 with multiplication. And so if I give you an element of the group and a point in the Stiefel manifold, I can just multiply each vector Vi by the corresponding lambda I. And this, you can check that you get a very nice point in this space. So this is an action of Z2 to the K on the Stiefel manifold, and it's a free action of this group on Vk to 2, meaning that unless you're multiplying by the trivial element of the group, you don't have any fixed points. You're not leaving anything fixed on the Stiefel manifold, which is something really useful for topological results of this type. If you want something similar to this, maybe you don't like the Stiefel manifold, you can use this space. So I'm just taking the space because it has K coordinates, and the dimension of the space is the same as the one for the Stiefel manifold. I'm just constructing it this way. To choose x1, you have this many dimensions. X2, you have D-2 dimensions, and so on, right? And you can have a similar action of Z2 to the K on this group by doing precisely this. So the big topological tool we're going to be using is the following result, that every continuous Z2 to the K equivariant map from this Stiefel manifold to the product I just told you has a 0. Now, if K is equal to 1, this is Borsuk Ulam, because here we have a sphere, and here we just have the first term, and so we get exactly Borsuk Ulam. So this is like an extension of Borsuk Ulam. And Chan, Chen, Frick, and Hull, they proved this using some clever topological invariant regarding the sum of degrees of some maps between spheres. And if it's odd, you guarantee zeros. If it's not odd, then maybe not. And for maps like this, they could check the parity of that invariant. If you are familiar with the Fadel-Husseini index, that's another topological invariant that was proposed in the 80s by Fadel and Husseini, and it's very used in this sort of in this area where you want extensions of Borsuk Ulam type results. And if you read actually their original paper from 1988, they prove something slightly different than this, but their proof implies this directly. So even just throwing those tools there. And one of the things I did with Michael, we didn't know that this was already proved, so we proved it using a very simple proof where you just basically need to do a homotopy argument, which I won't talk about today, but it's a proof where you basically need to know almost nothing about topology. Okay, so the only thing I want to convey is that this sort of results, you can throw many different things at this and prove it, and you can prove it with very elementary methods. Okay. Okay, so how do we use this topological version of Borsuk? Let's go back to the fairy bread sandwich. So the theorem was this, right? If I give you a permutation of the numbers from D to K, and I tell you this, you have this many I-dimensional mass assignments for each I, then you can find a full flag where each SI has all the measures on the next affine space. Okay? And somehow I want to parameterize the space of partitions with a Stiefel manifold, construct a function to the space, and then show that a zero of this function implies the conclusion of this theorem. So here goes the proof. The first thing I'm going to do is, for each dimension of mass assignments, I'm going to take away one and set it apart. Okay, so I take a measure, a D-1 mass assignment, up to a k-dimensional mass assignment, and I take them aside. So I look at how many measures I have of each of the others. So how many measures I have left. So tau I-1 is just going to be how many I-dimensional mass assignments I have left. Okay, and so I have this vector here, which is now a permutation of this because I took one out of each dimension. And then I'm going to take inside some Stiefel manifold that has as many elements as having one corresponding to each of those. Okay, so I'm going to be looking at this Stiefel manifold, and I want to construct this. So I think it's easier to do it with an example. So this is going to be my vector. So what I have is one measure on R3, two-dimensional mass assignments, and 0 mass assignments on lines. Those are aside from the ones I already took from each dimension. Okay, and so if I give you an element V2, V1, V0 in this Stiefel manifold, what I'm going to do is construct first my space of my set of nested affine spaces. So the first thing I do is I want to find S2, the plane. So S2, so I have my 2 here, I go to tau 1. I'm sorry, I go to S2, I go to tau 2, which is 1, so I look at V1. And orthogonal to this direction, I'm going to take a plane that has the measure I put aside. Okay, so this plane is having the measure mu2, 0. And then I go to the line here. So what I'm going to do is, this is now of dimension 1. I go to tau 1, which is 2, so I take V2. So in V2, now I take a line orthogonal to this that splits the measure I set aside that should be living here. And then I go to I want to construct the point that the 0-dimensional one. I basically have two choices for this one, but I have already, so I have this V0. And so I take a point that has the measure I have on S1. So for any V2, V1, V0, I construct S2, S1, S0 using these things that I set apart. Okay? And then I have to construct a function that tells me how am I splitting the rest of the measures or the rest of the mass assignments. And those are going to be the vectors here. And so x tau I tells me how SI splits the tau I mass assignments. And that's basically doing something similar to what we were doing in the proof of the Ham-Sandwich theorem, where you would say, for example, this plane, for each of the measures that are left, in this case, I'll have just one measure left. I'll just check mu of this minus mu of this. And this will be the entry in the R1 spot. And so you have to be very careful about things lining up with the indices. But when you construct this, and if you do it carefully, it turns out that if I flip any vector here of, say, V2, V1, V0, if I flip, for example, minus V2, V1, V0, I'm flipping this vector here to this. And so the only thing that's going to be changing is not the subspaces I'm constructing, but just the names of S1 plus and S1 minus. So if I was already assigning names to the sides of each of those things, I'm just changing the names of the red things, which is just going to change then the sign of the coordinate in the corresponding place. And so it turns out that this function is equivariant with this action of Z2 to the K. It's really the big bulk of the work is just checking that things align as you expect them to align. And so you'll have a 0 of this function, and that's going to be the set of partitions, the set of nested spaces that you expected. Okay. So if you like details, that's something you can check later. But one of the things you can do with this is that you can improve results about partitions of k-dimensional mass assignments where I'm not using mass assignments of different dimensions. So we can impose additional geometric conditions on previous results we had. So for example, Patrick Schneider showed that if I give you the k-dimensional mass assignments in RD, you can always find a k-dimensional affine space where all the measures can be split by a hyperplane. We can do this by imposing that the k-dimensional space we find contains the origin and k-1 fixed directions. So you can impose a lot of conditions on the space you find here. And this was conjectured by Schneider. He could prove it with d minus k plus 2 in here instead of d. And so let me just show you how the fairy bread sandwich theorem implies this. And you're going to be using this permutation, k plus 1 up to d. So we have k measures, k plus 1, d minus 1 mass assignments up to d, k-dimensional mass assignments. The only important thing here is that this is at least k in each entry. And so we already given the k-dimensional mass assignments. We can take anything we want for the previous mass assignments. So for the k mass measures I want here, I'll place a sphere centered at the origin, and then a sphere centered at each of the directions I wanted here. So the first hyperplane that has all these measures has to go through each of the centers of those spheres. And so it has to go through the origin and have the directions I wanted. And then you can define the next one. Actually, I'm only using k of them to reimpose this condition on the next on the d minus 2 dimensional affine space. And then you can do the same thing to impose those conditions in the d minus 3 dimensional affine space. And so you keep doing this until you impose those conditions on Sk, and then Sk minus 1 is just going to split the mass assignments you started with. Okay? So basically, the Ferry-Braid sandwich theorem just tells you that you can easily do this by imposing those conditions you want. Now, let me tell you about central transversals. We mentioned this in the plane or in dimension 3. In general, if I give you a number lambda between 0 and d, a lambda transversal of a measure mu is going to be a lambda dimensional affine space, so that every half space that contains it has a lot of the measure mu. So has at least this fraction. Okay. Now the big theorem by Shivaljevich and Frechika and Dolnikov is that for any lambda plus 1 finite measures, there exists a common lambda transversal. So for example, when lambda is equal to 1, that's the thing about any two measures have a common line transversal. When lambda is d minus 1, this fraction is 1/2. And so you recover the Ham-Sandwich theorem. When lambda is 0, this is 1/d plus 1. You have a point. And so this is the center point theorem. You have, for any one finite measure, you have a center point. So this is something that sort of interpolates between the center point and the Ham-Sandwich theorem. And the proof, to prove this, you usually have to know something more about topology. You have to do something clever about it. But using this Borsuk-Ulam type theorem about Stiefel manifolds, you can actually prove this quite easily. You just take an element here in this Stiefel manifold, and what you're going to be doing is projecting each measure onto the span of those, okay? And you're going to take pi, the center point of the projected measure. And so what we want is all these projections to coincide. It's a bit similar to what we were doing to find a center line in R3, where we projected, took a center point, and took the inverse of the projection. And to do this, we're going to construct a function. We're going to be doing the following. So these are my elements in the Stiefel, representing a point in the Stiefel manifold. And so what I'm going to do is to take the vector, say p1 minus p lambda plus 1, the difference of these two center points, and write it using this as my basis in the span I mentioned. Okay, so this is a point in the span of these vectors. I can write it as a linear combination of these guys, and I'll write the coefficients needed here. And then I'll do this for p2 minus p lambda plus 1 up to p. Okay, so I have enough space to put all, and then the rest I'm going to just fill with zeros. And what happens here is that since these are orthonormal, since these are orthonormal vectors, if I write a vector in that basis, the coordinates are just these dot products. Which means that if I change any one of this, if I flip the sign, the span doesn't change, so these vectors don't change. And so this dot products, the only thing that changes is this, whether I change its sign or not. So this is an equivariant function, meaning that it has a 0. And so what happens with a 0 here? It means that all these vectors have to be 0. So p1 is equal p2 equals p3. Okay, so you can simply prove the central transversal theorem using this result. Now, you might say, okay, you're wasting a lot of information here because you just filled it with zeros. So if you don't want to waste information and you don't want to fill it with zeros, you can be a bit clever about using that extra space and prove this extension of the central transversal theorem. So now I'll give you d measures instead of just lambda plus 1. And I'll find subspaces that do this, so nested subspaces, so that S lambda is a lambda transversal for the first lambda plus 1. That's the central transversal you usually guarantee. But the next ones are lambda. So S lambda plus 1 is a lambda plus 1 transversal to the next measure. And the next one is a central transversal of that dimension to the next measure, and so on. So you get to complete, in some senses, central transversal. One thing that I really like about this is that the number of measures you have here is equal to the number of measures you have in the Ham sandwich theorem. So you never have to give those up. You just have to treat them a bit differently. This one, you can prove it using the central transversal theorem if you're stubborn about this, because you can find S lambda, and how you extend to S lambda plus 1, S lambda plus 2, and so on. You can get those extensions using, again, the central transversal theorem. So you can bootstrap that one as well, or you can be a bit clever with this proof. This proof makes it a bit easier to see that you should be able to do that. Okay. And one theorem that you cannot bootstrap the central transversal to is the following version. So I'll give you d finite measures in ORD. We're going to find two hyperplanes, H1 and H2, so that their union splits the last measure into 4 pieces of the same mass. And their intersection is a d-2 central transversal for the first d-2 measures. And H1 has, so the thing about this is that when you project to a plane, these 2 lines I told you about that cut into 4 equal pieces, they actually can be used as, say, p lambda plus 1, the point of intersection. And you can see that it changes, that if you flip the signs of v1 and v2, then you get this equivariance as before. So a similar idea to this one shows that you can get this extension of that, which is the result I mentioned at the beginning. And so right now it seems a bit that the results I told you about central transversals, like the type of things I did with Ilani and the sort of things that I did with Michael are a bit separate from each other. So we can try to combine them and talk about central transversals and mass assignments. Or now, instead of trying to find a common halving line or halving hyperplane to these things, I want a common central transversal. And what I want is not to get more measures than the Ham sandwich theorem allows me, but to use more measures than the central transversal theorem allows me to. And of course, this was already done by Schneider. So he got this version of the central transversal theorem where you have this many k-dimensional mass assignments. Then in some k-dimensional, actually he used a linear space, you can find a, they all share a lambda transversal. So if k is equal to d, this cancels, you just get this, which is the usual central transversal theorem. If k is if lambda is k minus 1, you get the Ham sandwich result he proved for mass assignments. So this is sort of the excess you get in terms of this thing. Now this one, I told you how we could improve it by imposing geometric conditions and asking things to have at least k minus 1 directions fixed and going through the origin. So we can do the same thing here. And it's the same thing, so we just get it to be lambda vertical, meaning that it goes through the origin and has this lambda directions fixed, which we can impose, which is a new thing. And this is sort of a combination of 2 proofs I told you before, where you have to use a different Stiefel manifold, and you'll use a block of those coordinates to guarantee that the projections you would usually use in a proof of the lambda transversal theorem coincide. And then the other coordinates you have here are the ones you get for free to impose those geometric conditions as we were doing before. So the fact that we get here a height lambda in the height of x d minus lambda means that we can impose lambda conditions in some sense. So I will just hand wave around this and tell you, if you place the coordinates correctly, you can combine the two proofs I told you about before. Okay. And now, so this, I've been speaking for about 1 hour. I want to tell you a bit more about transversals to partitions. So you mentioned that it could be a bit more than 1 hour, right?
It's okay, yeah. We can, you can speak as much as you want, so we have time.
So furthermore, before I jump into transversals to partitions, is there any question about this so far?
I have no questions. Okay. It's very clear.
Good. So let's jump into this, because I want to go back to the example I gave you in the plane and say, okay, we said that we really wanted to talk about this point as a center point and that we could do better, but maybe we really like this partition. Maybe you really like the fact that we're splitting with these two lines into 4 equal pieces. And so every closed, the fact that every closed half plane contains one of the 4 regions actually means that every line I draw misses the interior of at least one region. So in this case, I'm not hitting the interior of this region here. And so this is the type of things that Yao and Yao wanted to improve on in 1985. They wanted to have partitions of a measure into equal pieces so that every hyperplane missed some of them. And so what they showed is that for any measure mu in RD, there's a partition of RD into 2 to the d convex pieces of equal measure, so that every hyperplane misses the interior of at least one region. And this is a bit of how their partitions look like in dimension 3. In dimension 3, if you cut using 3 hyperplanes into 8 equal pieces, it also satisfies this condition. But this is not something you can do in dimensions 5 and higher. But if you just ask for this, then this is possible in any dimension. And this is it's motivated in computational geometry by doing what they call geometric range queries. So I won't go into the applications of this, but I want to go into diving a bit deeper into the structure of these partitions, because they prove this with a very, very strange. Proving this has a very different proof from what you would usually see as a proof of a ham sandwich type result, where it's not using the test map scheme. They used induction on the dimension. And in each induction step, they use the Borsuk theorem. So it's a really different proof for use of partitions. And I think it's really worth studying what actually happens here. So the partition actually depends on the measure and an orthonormal basis of RD, which is also good news for us because it's hinting at Stiefel manifolds. And every partition has what they call a center. In this case, it's this point, which satisfies some properties. So if you give me the measure and the basis, I'll give you the partition, and I can tell you where the center is. And their proof, let me give you the idea behind the proof of this Yao partition theorem, is we do this by induction on D. So for D equals 1, this is trivial. We just pick a median of the measure in the line. And that median is our center. Now, if I know this holds for D minus 1 and I want to prove it for D, I'm going to take a hyperplane orthogonal to mu D that has the measure. So the top and the bottom, they have half the measure. And then I'm going to look at the measure on the top, and I'm going to project it onto the plane using a direction vector V. So I make it rain until on this plane, I'll get some measure here. And then the bottom part, I'm going to also project it onto H using the same direction V. And so I'll get 2 measures on this H. Okay? And then I'm going to use the vectors u1 up to ud minus 1 as my basis of H, and find a Yao-Yao partition for the top and the Yao-Yao partition for the bottom. Okay? And this is the key part here. If we are lucky enough, the centers of these two partitions coincide. So this point and this point, we want them to coincide. If they coincide, then we just take the inverse of each partition, and we get this Yao-Yao partition here. And so in this case, this is my my direction in which I was projecting. And so, for example, the partition I got for the top was these two, which were these two lines here, the plane, and the partition we got for the bottom were these two lines, which correspond to this line and this line. Okay. Now, how do we guarantee that we can be lucky? That's where the Borsuk-Ulam theorem is used, and they prove that the direction V that you make things rain onto H always exists and is unique. Okay. So let's look a bit into this proof here. The first observations is if we change the sign of any of these vectors, the partition does not change. You prove this by induction. If you flip this UD, then the first halving hyperplane doesn't change, and then by induction, the previous one didn't change, and by uniqueness, you get exactly what you want. Then, if I take V lambda, the span of U1 up to U lambda, going through the center of the partition, it's in the boundary of all bridges. And this also, you can prove it by the induction argument. I really care about the case lambda equals 1, because then we get this single line in the direction of U1 in the boundary of all the bridges. Okay. Usually, the analysis of the Yao-Yao partition, it goes along analyzing the line in direction V, but we don't have that much control over that. But U1, we have absolute control over. Okay. And the other thing is you can play a bit with the induction. So, for example, in the first step, instead of taking a point that splits the measure in half, you can take 2 points, 2 non-negative points whose sum is equal to 1, and make the left side half measure alpha and the right side to half measure beta. Then in the next steps, you do it exactly as Yao and Yao did. And what you end up with is having a partition where in the direction of U1, every region on the left has size alpha over 2 to the d minus 1, and on the right has beta over 2 to the d minus 1. So that's for all the measures on that side in terms of U1, like this. Okay. Actually, I think Lehec had a different proof of the Yao-Yao partition where he played a lot more with this idea, but we only care about changing the first step. Okay. One thing I didn't mention here is that then you also prove this property about the hyperplanes missing regions, and that also goes into the induction. Okay. So first thing, I told you about this vector V lambda, and that I've told you a lot about central transversal theorems, and you also have this equivariance of this flipping signs. So it's tempting to use this V lambda in the central transversal theorem, and that's actually something that happens here. If I give you lambda plus 1 measures, then there's a Yao-Yao partition of this, so that V lambda in this Yao-Yao partition is a lambda transversal for all the other measures. That's also the in dimension 3, the result I told you about 2 measures, and for one you'll have 2 planes who's split into 4 equal pieces, and then the intersection is a center line for the other one. Because if you ignore in here the green sections, that's a partition in the plane in R3 into 4 equal pieces. So you can combine Yao with the central transversal theorem. And this one, I don't know how to prove it with the fancy topological tools you would usually use for the central transversal theorem. And the other thing you can do is so I told you about these partitions with alpha, beta. And one thing you can think is take a plane here that's orthogonal to U1, okay? It turns out that if I look at the regions I have here in this partition, I have the ones closer to that. Okay, so take this region, and then if I take this region here, say, I hope it makes sense. So those two, they get projected to the same thing when I project onto this space. Let's call it H. So if I actually ignore the green sections, what we get here is a partition into 2 planes of the projected measure. And this turns out to be a Yao partition of the projection, or the regions in the Yao partition of the original measure are just paired up and projected to the same thing. And so using a bit this idea, we can actually play a bit with the Yao partitions, or in the first step, we could take, for example, a partition of side, instead of alpha beta, or 1/2, 1/2, we could take 1/3, 2/3. So we get a partition with just the green here, and this a blue thing, and we get that each measure on the right of a region on the right is twice as much as the corresponding one on the left. And then if I just look at the regions on the right, I can do a Yao partition of them, starting with 1/2, 1/2. And so you're introducing these yellow things here. It turns out that the blue things, they stay the same. So I'll call the blue things the frame of the partition, and the other things the wings of the partition. So you're introducing these wings here. And one cool thing about this partition is that every hyperplane intersects this line in one of those 3 intervals, right? Either on the left of both centers, between both centers, and on the right of both centers. And one thing that happens here is that if you intersect that line here, you're missing one of the regions, sort of in the middle regions, and one of the regions on the right. If you intersect that line here, you're missing a region, the interior of a region on the left, and one of the regions on the right. And you intersect that line here, we're going to be missing a region on the left and one of the middle regions. And you can sort of keep doing this. So we get this result here that for any t and any measure mu, the superpartition of RD into this many convex parts of equal measure, so that every hyperplane intersects the interior of at least t regions. For t equals 1, this is Yao, and this is exactly the Yao partition. We're doing nothing new here. For t equals 2, this is an old result I had with Edgardo Roldan Pensado. Our proof was very different from this. It used Yao, but we were focusing on something different. And for large t, this is new. If you fix a dimension and make t really, really big, this stops being good at some point, because it's better to just iterate Yao. To use a Yao partition, and then a yaw-yaw partition of each section, and then a yaw-yaw partition of each section, and so on. But if you fix T and you make the dimension become big, I think this is the best node. So we usually want to minimize this number here. And so this is something we get. I think at this point, yeah, this is the point where I'll stop. So thank you very much for your attention today.
Okay, Pablo, it was very, very interesting. So we can unmute us and upload to Pablo, if you can. Okay. Do we have questions? Okay. I have a question. Pablo, you said that from the first ham-sandwich type result follows the central line theorem, yes? This result by Dolnikov and some Serbian people. I have a question. Are there some kind of discrete applications, some kind of unexpected discrete versions of meaning that the standard ham-sandwich theorem we can state in a way that we have say in the plane we have n red points and blue points, and we can partition them by a line. But maybe are there some kind of similar statements or some similar discrete versions, some discrete corollaries of your first result of the ham-sandwich type result?
So every ham-sandwich result we used it, or we applied it to smooth measures. Now the original ham-sandwich, say for mass assignments that Patrick proved. Let me see if I can get back to that drawing. Actually, maybe I can go back all the way to the beginning. So Patrick was interested in the motivating example was with families of lines in R3, discrete families of lines in R3. And so one cool consequence of his result was that if I give you in R3 a bunch of red lines, a bunch of blue lines, and a bunch of green lines, so if I give you any two lines, say this two lines like this, unless you're really unlucky, there's going to be a unique vertical line that intersects both of them. And so I'm going to say that this line is below this one, so that this line is below this one, if the unique vertical line intersects this one first, and then this one further up, okay?
Okay.
And so what he showed is that if I give you a discrete, so three discrete families of lines in R3, there's going to be an additional black line so that it's above half of the red lines and below half of the red lines. It's above half of the blue lines and below half of the blue lines, and also for the green lines, above half and below half.
Mm-hmm. So it's kind of...
So it's like a ham sandwich for lines, but your splitting object is a line.
Yeah, but you also somehow fix a direction of splitting, meaning that you consider vertical lines, yes, with respect to which you partition. So, Okay.
So this would be the what I would call maybe the unexpected discrete consequences of those results. Use applications of the central transversal theorem to say purely discrete problems. I don't know any at the top of my head. I would want to give you something like the necklace splitting problem, but because that's one very striking applications of the ham sandwich theorem, but I don't know any like this for the central transversal theorem.
Mhm. Okay, that looks nice. Yes. And similar applications, I think, holds for not for lines, also for some planes. Yes.
Yes. Yeah. So if I give you instead of families of lines in or three families of k-dimensional planes in or D, then your splitting object should be a D minus K minus 1 space. You'll have a vertical direction.
Mm-hmm.
And so it looks a bit like hand sandwich check results on Grassmannians, if you think about it that way. But yeah.
Thank you.
How are you, Jonas?
I am fine. Thank you very much. I enjoyed this talk very much because I like the original how we could use it, and it's a very nice generalization. I really congratulate you.
So I think my biggest surprise here is that for me the central transversal theorem was always a bit mysterious in the sense of the topological tools you have to know to prove it. And so the fact that you can use this Borsuk Ulam theorem, which can be proved easily, really clarified a bit this sort of thing. So it seems that going from the Grassmannian to the Stiefel manifolds should make things more complicated, but since you have this basis to sort of hang on to, it actually simplifies the proof.
Yeah.
Nice proof.
Thank you, Pablo. Thank you. It was really interesting.
See you. Thank you for the invitation.
It's already available on Archive, yes?
Yes. So it's actually what I talked about is two papers, one with Michael and one with Ilani, and they're both on Archive. Yeah.
Good. Thank you. I will take a look.
Okay. Well, I'll see you later then.
See you. Okay. Bye-bye.